Hello, in this video I'm going to go over resistance in series and parallel. This isn't too complicated of a subject, however I'm going to break it into two parts. This will be explaining how the resistors work in parallel and series, and I'm also going to break it up into how to find the different problems like this. So I'll probably have this video, then another video explaining how it works with junctions, which I'll explain in a second, and then I'll probably have two examples in another video, and I'll try to link them all together to help you out. Okay, so first I'm going to go over resistors in series. Take a guess real quick, see if you can figure out which one's going to be in series. Correct answer? It's going to be this one. And so what we have are two resistors right here and here, and a current going around at a constant rate like this. And that's because they're all connected in series. So this will just be I. And there's no junctions or no points which the current could take, paths off of, like if it went this way or this way. There's only this, then this. So I has to equal I. And it goes all the way around like that. Everything connected has to have the same current running through it unless it's in series. Okay, so we have this change of potential, and we know something. We know a few things about circuits and resistors already, and that's change in V is equal to IR, and that's Ohm's law. And so we have this change in V right here, and this current, which is just one. So, and then we have these two resistors. Now, we find them by doing this. The change in V is divided by I is equal to R. Now, in this case, it's all the R's, or REQ. The EQ stands for the equivalent resistance of all of them together. And for resistors in series, we can just combine them together. This would be like having a resistor of R1 plus R2, and that's because they're all connected. So since these two are constant, this one also has to be constant, and because the current is running through both of these, it'll be REQ is just R1 plus R2. So in series, all we have to do is add up all the resistances to get the total R in Ohm's law. And if you want individual potentials across them, since you already know the REQ, you can take the current times, actually you don't need REQ, you can take R1 times the current, and that's equal to the change in voltage. So you should always be able to find and I put the 1 here for the change of potential across 1. You should always be able to find, in series, one variable as long as either both resistances are defined, or the potential is defined, or the current is defined. You need two variables obviously defined, but you should easily be able to find it. Now, for number 2, this is parallel. So what we have here is this current going around. I'm just going to call this I, and then what we call a junction right here. So this will be I, and now the current has to split. Some will go this way, some will go this way, and they'll each choose a path and based on the amount of resistance. Now how we solve these problems is fairly interesting. So we have I1, or I2 right here, and I1 right here. And what we do is we know that I has to equal I1 plus I2. You can think of that as like a conservation of current. We also know that the maximum potential is equal to right here, because that is the only thing changing the potential. We also know one other thing, that the potential up here is potential 1 and potential 2. If we take potential 2 minus potential 1, we will get the change in potential. That's because if you can think of this as a high point up here and a low point down here, even though these resistors could be different, the potential across them still has to be the same. Right here, here, and here is where this V1 is maintained. Right here, here, and here is where V2 starts. So the change of potential has to be the same as the change of potential 1 plus the change of potential 2. And in parallel, we now know that the change of potential is going to be the same, across both resistors. We know that the currents are different, but we also know that from over this example over here, I'm going to change colors now. We know that I is equal to, if we just look at Ohm's law, we know that the change of potential divided by Req is Ohm's law. So this potential is going to be different. There's going to be I1, I2, we're going to have that in there. However, if we just take this part right here, we have the change of potential divided by R1 plus the change of potential divided by R2. These two are going to be 1 and 2. These two are going to be the same, so they're just going to cancel out, which is going to be equal to total potential divided by total Req. If we divide all of this by the change of potential, since all these are the same, they'll all cancel out. So we have then the parallel, how we calculate resistors in parallel. We have to take the inverse is equal to the inverse of resistance. We do that because of right here. Since the current is not constant, the current is changing for each of these individual, because of these junctions, they're changing. We're not gonna have the current in most cases. We're going to need to solve it using the potential instead of the current. So now we have these. We can take, for example, this current 1 is equal to the change of potential 1, which is just the change of potential in general, divided by R1. If you don't know why I use the change of potential normal, or why I said that, it's because all these change of potentials are going to be the same. I don't think okay. This shouldn't be a plus right here. This should be an equals, and I'll edit that in, and yeah, but that was the issue. Should be 0. I'm sorry, I got that wrong. They're all going to be equal to each other, so this can be change of potential 1, change of potential 2, change of potential 3. It's for what I said, because all this will have the same potential, and then all these down here will have the same potential. So this is how you calculate the different currents running through it. And if you have the different currents, you get to calculate the different resistances, etc. And these currents will continue. This will be I1 and I2 all the way around. And they will recombine down here to create just I again. So this and this will be equal. This will be I2, and this will be I1. I hope this helps explain this for the most part. Like I said, I'll have some other videos explaining how to solve these problems, and a little bit more probably on junctions, because people seem to have trouble with that. However, on my website, I will probably write a couple of guides, or at least a short explanation. And I hope that I've helped. Feel free to comment, and I'll respond. And if you feel the need, I'll even create a new video. Thank you for your time, and hope you enjoyed my video.